This video is about AVL trees. We're going to go through the rules, and then I'm going to do example 1, which is posted in it's the output of a program I wrote many years ago. So it's not as easy to take a look at that posting. It's not as easy to read the numbers, but they are correct, and it's good to kind of check your work as you go along. There are also, if you Google AVL tree animations on YouTube, you'll find all kinds of real cool animations. And those are great to check your work. But for your homework, I still want you to do what I'm going to do here with this hand execution thing. All right, so the first thing I would refer you to is the rules on page 77 of the notes. Okay. So we have two kinds of rotations. There's a left-left rotation and a left-right rotation. There's also the mirrors of these. So there's a right-right rotation, which is just the same thing, but everything flipped. And then there's a right-left rotation, which is just this thing, but everything flipped, like as if it were in a mirror. Okay, here's the rules. So first thing you do is you find the insertion point. That is, you insert the new node. And then you backtrack up from the insertion point where you put the new node, and you find the pivot node. So the pivot node is the first node up from the new node with a non-zero balance factor. So you have to keep track of these balance factors on every node. And a balance factor is just how long a tree is on one side versus the other. So like this has a balance factor of 0, and this if this has a length of 2 and this has a length of 1, so it's 2 minus 1 has a balance factor of 1. And this guy has a length of 1 on this side and a length of 2, so it's 1 minus 2, so it's minus 1. Okay, and if any node gets a balance factor of more of 2, really, then it's time for a rebalance. Like, for example, this one, the length on this side is 1 and the length on this side is 3. So 1 minus 3 is minus 2. And that means we need to do a rotation. We need to rearrange these guys so that it looks like that. Okay, so that's the pivot node, and the pivot node is the first node up from the new node with a non-zero balance factor. You'll see on the example. Okay, then after you found the pivot, and this is where students mess up a lot, so I'm emphasizing this. You find the pivot first, then you update the balance factors for nodes between the new node and the pivot, up to and including the pivot node. So find the pivot first, then update the balance factors in between the new node and the pivot. Then you look at the balance factor at the pivot, and if it's plus or minus 2, it means that it's heavier on one side or the other, so you need to do a rotation. So you do one of these rotations, and then after you've done the rotation, you update the balance factors on the nodes that you've pivoted. These lettered nodes you'll see in a minute. Okay, so I'll show you, examples. So here's the left-left rotation. You're going to find the pivot. And so referenced from the pivot, you're going to have these two lettered nodes, A and B, with this orientation. And then you'll have these subtrees that are connected off of A and B. So you'll do a left-left rotation, and A and B will change position like this. They'll go from A on top and B over here to B on top and A over here. And then you'll reconnect the subtrees. So this is after the rotation. Then you see step 4 here, you update the balance factors after you've done the rotation. Okay, that's that. And you'll see in an example how that works. All right, then the left-right rotation, you're going to find the pivot. And then you'll look down on the way that towards the new node, which is somewhere down this path. And you'll see there'll be these lettered nodes, A, B, and C. And the first turn down from the pivot is left, and then the second turn is right. So we call it a left-right rotation. That's where the name left-right comes from. Okay, there's A, B, and C. Then there's these subtrees, tree 1, tree 2, tree 3, and tree 4. Okay, if you have a balance factor of 2, this rule, then you need to do a rotation. So you'll rearrange these lettered nodes, this A, B, C, to this arrangement, and you'll reconnect the subtrees across the bottom, and you'll update the balance factors after the rotation here. So C will always have a balance factor 0. B and A will have these balance factors according to these rules. But we can just look and see. For the hand execution, we can just look and see what these balance factors are. Of course, if you were coding it, you would need some rules like this. But we're not going to code it. We're just going to do a hand execution. All right, so those are the rules. So we'll keep these right here because they're good to look at. And I will do this sequence 1, which is this document here that's posted. And I'm going to keep it over here because, just sort of check my work, all right? So example 1 has this insertion sequence 9, 8, 7, 6, 5. You can see it's going to get way unbalanced and several rotations are going to be needed. And then 1, 2, 3, 4 more sequential stuff, which results in an unbalanced tree. This guy, it has a left, left, a left, right, a left, right, and a left, 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 then a left, right, and a left, right. Okay, so let's get started. So node number 9 comes along and you insert him into the tree. That's the insertion point. That's find the insertion point. Then the pivot is the, so this has a new node always has a balance factor of 0. It has no children, so it's going to have a balance factor of 0. So that's the insertion point. It's a trivial case for the root, but you found the insertion point. Now we need to find the pivot. Okay, the pivot is the first node up from the new node with a non-zero balance factor, or the root. So the pivot is this. Okay, then you update the balance factors. Still 0. Nothing to do. Done. So let's do the next insertion here. Let's insert the 8. So okay, got 9 has a balance factor 0. We put 8 in there. 8 goes over here because it's the new node. So we found the insertion point, and all new nodes have a balance factor of 0. Okay, then we find the pivot. So the pivot is, according to this rule right here, the pivot is the first node up from the new node. Here's the new node. The first node up from the new node with a non-zero balance factor, or the root. So in this case, it's the root. Okay, then you update the balance factors for nodes between the new node and the pivot. So in between here, we update the balance factors. This guy is still 0. This guy, the balance factor is going to be 1 because it's longer on, the branch is longer on this side, but by 1 than this side. All right, so it's not a 2, so we don't need to rotate, so we're done. So let's redraw. This is our tree now, okay? The root is 9, and it has a balance factor of 1, meaning that it's longer on, the left branch is 1, has a length of 1, and the right branch has a length of 0, so it's longer on the left by 1, balance factor of 1. And this guy has a balance factor of 0. Okay, then we insert 7. So let's just do a regular binary tree insert, which is what we're doing. The inserts haven't changed. AVL tree just adds these rotations to keep the tree balanced. Anyway, so to do insert 7, we start here. 7 is less than 9, we go that way. 7 is less than 8, so we go that way. So 7 goes here. That's the insertion point. Find the insertion point. And this is a new node. All new nodes have a balance factor of 0. Okay, then we find the pivot. So the pivot is the first node up from the new node with a non-zero balance factor. So we start going up looking for a non-zero balance factor. We find it here. This node is the first node with a non-zero balance factor, so it's the pivot. Also happens to be the root. All right, Then you, after you found the pivot, you update the balance factors for nodes between the new node and the pivot, including the pivot node. So you start here and you start doing the balance factors. This is going to have a balance factor of 1 because the left branch has a length of 1 and the right branch has a length of 0. 1 minus 0 is 1. This has a balance factor of 2 because the left branch, the longest branch on the left, has a length of 2. And the longest branch on the right has a length of 0. So 2 minus 0 is 2, right? Just to be more accurate, 2 minus 0 is 2. So that has a balance factor of 2. That needs a rotation. Rotate, see, it's rule 3. Rotate if the balance factor for the pivot is plus or minus 2. Here it's plus 2. So we need to do a rotation, all right? So look at your rules here. We have this situation. We have left, it's going to be a left, because this is the pivot, and the first 2 turns down from the pivot to the new node are left. So it's a left. Okay, then this is node A, this is node B, right? A and B. This is subtree 1. This would be subtree 2, which is null. And this would be subtree 3, which is a null tree. Okay, so we do this left thing where A and B switch positions like this. So B comes up here and A goes over here. They're both going to have balance factors of 0. Okay, B is 8. I'll put the B here, and I'll put the A here, and A is 9. Okay, and then you hook up the subtrees in the left to right, tree 1, tree 2, tree 3. So this is tree 1, which is 7, and its balance factor. Tree 2 and tree 3 go here, and they're null. They're null trees. So this is the, after the rotation, A and B have a balance factor of 0. So that's what these zeros come from. It just works out that way because the guys who invented this, these guys, were geniuses. So I'm just going to redraw because it's getting messy. So there we go. That's redrawing this thing. Okay, so now it's time to do this guy, 6. So I'm going to insert a 6. So the 6 is going to go here. That's the insertion point, and the balance factor is 0 because it's a new node. Then I go up looking for the pivot. The pivot's going to be here because it's the root. Remember, the pivot is the first node up from the new node with a non-zero balance factor, or the root, should say that, or the root. Okay, so here it's the root. Okay, then you do step 2, after you found the pivot, all right? Students mess up there a lot, so I'm emphasizing it. But first you find the pivot, then you update the balance factors between the new node and the pivot. So this is going to have a balance factor of 1. This is going to have a balance factor of 1. This one is 1 because it's 1 long on the left and 0 long on the right. So 1 minus 0 is 1. This one has a balance factor of 1 because the longest branch on the left has a length of 2 and the longest branch on the right has a length of 1. So 2 minus 1 is 1. Okay, that's not plus or minus 2, so no rotation is required. So I'm just going to redraw just to clean this up because it starts getting crazy. So there's our tree right there. Okay, so we insert, it's time to do 5 now. So 5 will go here. It has a balance factor of 0 because it's the brand new node. The pivot is going to be the first node up from the new node with a non-zero balance factor. This 1. Now, this is before you update the balance factors. So you find the pivot. It's the first non-zero balance factor. Then you update the balance factor. So this is going to have a balance factor of 1. This is going to have a balance factor of 2 because the longest branch, down from 7, the longest branch on the left is 2 and the longest branch on the right is 0. So 2 minus 0 is 2. This is rule 3. The balance factor is 2, so we need to do a rotation. Which rotation do we do? Well, we go down from the pivot towards the new node, looking at the turns that we make. And the first 2 turns are left and left. So this is a left-left rotation. Okay, just like the last one. So if this is a left-left rotation, then looking at this pretty thing here, then this is A, this is B, this is subtree 1, this is subtree 2, this is subtree 3. So these guys stay like they are. They don't even know what's happening. And node B goes over there, and node A comes over here. So here the orientation was A, B, A on top, and B this way. Now it's going to be B on top and A that way. The subtrees are going to be tree 1 here, which is 5, and tree 2, which is null, and tree 3, which is null. And B was 6 and A was 7. And for a left-left, A and B will always have a balance factor of 0. So this is 0, this is 0. Okay, so I'm gonna redraw this. I'm gonna redraw this thing. So it's 8, 9, 6, 5, and 7. Yeah, and it's as balanced as we can get it right now. Isn't that nice? It's a very beautiful thing, really. Okay, now it's time to insert 1. That's our next guy in sequence. So the 1 is gonna go, the 1's gonna go here. The balance factor is 0 because it's the new guy. The pivot, you go up looking for a non-zero balance factor. We find it here. Also happens to be the root, which is fine. Then, after you find the pivot, you update the balance factors between the new node and the pivot. So it's going to be, this has a balance factor of 1. This has a balance factor of 1. This has a balance factor of, so the length on this side is 1, 2, 3. The longest branch on the left is 3. The longest branch on the right is 1. So 3 minus 1 is 2. That means we need to do a rotation because we're out of balance by 2. So what do we need to do? Which rotation do we need to do? To determine that, we follow down towards the new node from the pivot, and the first 2 turns are lefts. So that means we're going to do a left-left. So we map what we got here to here, and this is A, this is B. All of this stuff here is subtree 1. All of this stuff here is subtree 2. All of this stuff here is subtree 3. So we're going to do a left-left rotation. So we have this AB orientation. Now it becomes this BA orientation. So BA and BA is 8, B is 6, subtree 1 is 5 and 1, subtree 2 is 7, subtree 3 is 9. After the rotation, A and B have balance factors of 0. And I think we're good. So I'm going to redraw this thing because, yeah. So 5 goes there, and 8 goes there, and 7 goes there, and 9 goes there. Yeah, it's balanced. That's great. So these are balanced. This is balanced. This is balanced. This is unbalanced. 5 is unbalanced by 1, and 1 is balanced. That's great. With that, all right, time to do insert a 2. So the 2, start here. 2 is less than 6. 2 is less than 5. 2 is bigger than 1, so the 2 goes here. and it has a balance factor of 0 because it's a new node. Where's the pivot? The pivot is the first node up from the new node with a non-zero balance factor. So you travel up towards the root on the way you came to, you go back the way you came. In reality, you would, if you were implementing this, you would keep several pointers, so you wouldn't have to backtrack. You would just go to the appropriate pointer. It's really efficient because you never have to travel more than the height of the tree for an insertion, right? Because it's a binary search tree, so you never have to go more than the height of the tree. And if you keep extra data along the way, if you keep extra pointers and these balance factors and all these things, you don't have to go back. That is, you don't have to traverse back. It's just some constant time operations to go back to those pointers and check the balance factors and then update some pointer values to rearrange the tree. It's just very efficient. It's a really a kind of a beautiful thing. I feel nerdy to say that, but that's the way I feel about it. I do think this is a pretty thing. Mentally, I know my chicken scratch is pretty ugly, but anyway, so we insert the pivot's here because it has a non-zero balance factor. Okay, then you update the balance factor. So this is going to be -1 because the length on the left is 1 and the rank 0. The length on the left is 0. The length on the right is 1. So it's 0 minus 1 is -1. This guy is going to be -2 because the length on, no, it's going to be 2. Because the length on the longest branch on the left is too long. It has a length of 2, and the longest branch on the right has a length of 0. So 2 minus 0 is 2. So because this is a 2, we need to do a rotation. Which rotation do we do? We look at the first 2 turns down from the pivot. So the first turn was the left turn, the second turn was the right turn. So it's a left-right rotation. So the subtrees are going to be, this one is null. Wait a minute. So this is A, this is B, this is C. Yeah. So this is subtree 1, this is subtree 2, this is subtree 3, this is subtree 4. You see A, B, C, and then the tree 1 hangs off of B, and C has 2 and 3, and A has 4, tree 4. So that we're going to do a left-right rotation. So much of this part of the tree over here stays the same. It doesn't know what's happening. It's clueless. Then these guys, A, B, C, this A, B, C, A, B, and C get rearranged. The way I think of it sometimes is C goes up to the top, B stays where it is, and A takes the remaining position here. Okay, so C is going to go up there, B is going to be here, A is going to be here. So this is going to be subtree 1, which is null. This is going to be subtree 2, which is also null. And this is going to be subtree 3, which is also null. And this will be subtree 4, which is also null. So A is 5, and B is 1, and C is 2. And our rule says that node C will always have a balance factor of 0. Why? Because AVL, Mr. A, Mr. V, and Mr. L were geniuses. That's my answer. These guys, B and A, are going to have other balance factors. In this case, for this hand execution, it's easiest just to look at the subtrees, and you can tell just by looking that these are 0 balance factors. All right, so redrawing this stuff just to clean it up. 6, 2, 8, 7, 9, 1, 5. Perfectly balanced. Everybody's perfectly balanced and fully filled at this time. Okay, last guy we did was 2, so it's time to insert a 3. So the 3, start here, smaller, bigger, smaller. The 3 goes here. It has a balance factor of 0. The pivot is the first node up from that new node with a non-zero balance factor, or in this case, it's the root. Then we update the balance factor. So this has a balance factor of 1. This has a balance factor of 1 minus 2 or minus 1. This has a balance factor of 3. The longest branch is 3 minus the longest branch is 2. So this is 3 minus 2 or minus 1. So no rotation required because we're not off by more than 1. So I'm going to redraw this guy here. So 6, 2, 8, 7, 9. There he is. All right, so now it's time to insert 4. I think that'll be our last rotation. It will cause a rotation. So we insert 4. So start here, 4 smaller, 4 bigger, 4 smaller, 4 bigger. 4 goes here. The pivot is this guy because it has a non-zero balance factor. You're going up. The first. Then you update the balance factors after you find the pivot. So this becomes length of 1 minus the length of 0 minus 1. It becomes minus 1. This one has a length of 2 minus 0, so it's 2. So we need a rotation because it has a balance factor of 2. The last 2 turns were left and right, so we need to do a left-right rotation. All right, so much of the tree stays the same. Okay, if this is the pivot, then this is node A, this is node B, this is node C. This guy stays the same, this guy. This. C comes on top. B stays where he is and A goes over here. The subtrees are all null. They would be here, 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 and here, but they're all null, which would end up here, 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 and here. This always has a 0, always. Okay, C is 4. B is 3 and A is 5. And then you can just look at the subtrees and see that these are balance factors of 0. And just redraw one more time and just to look at it and see, is it cool? Yes, it's cool, right? I mean, this guy's balanced, 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 4's balanced. This guy, heavy by 1 on this side. That's cool. This one, heavy by 1 on the left. That's it. All right. Hope you enjoyed this. I'll do one more. Okay. Thanks.